Hello. Hello and welcome to the second installment of the ExamRiz GCSE Maths live tutorials, coming to you live from central London, prime location for some prime GCSE Maths. So today we're going to be going over quite a few topics once again, hopefully trying to get through as many as possible, starting with SURDS. Now, in my experience, SURDS have been a problem area for many people, and I'm going to attempt to unlock the code for SURDS in its entirety today. So hopefully, from beginning to end, you should start off, even if you have no idea what the fuck SURDS are, by the end of this, you're going to know exactly what they are, hopefully. So as you can see, I've got this document lined up here. I'm going to actually zoom in really close to create a whiteboard for us because I want to just go through some sums with SURDS first. So the background of this, and bear with me if you already know this, but I do want to touch all bases with the people who really have no clue, because like I said, it is a genuine problem area for a lot of people. If we deal with algebra, for example, if we've got a sum that's like 3x plus 4x, looks like the pen is extremely thick right now because we're so zoomed in, but that's fine. So x plus 4x we should know equals 7x, because the idea is I have 3 x's, I have another 4 x's, I put them together and now I have 7 x's. Well, the idea with sums with SURDS is exactly the same. Let me try and see if I can narrow the pen here. Pen thickness is a lot thinner. Let's see. So for example, if we have 3 root 2 plus 4 root 2, that is going to be 7 root 2. For the same reason, we have 3 root 2s, we have 4 more root 2s, so together we have 7 root 2s. So when we're adding and subtracting SURDS, the laws of algebra apply in the exact same way as they do for SURDS and for algebra. So let's delete this stuff. And I'll do another example in terms of multiplying SURDS. So for example, when we're dealing with algebra, we have 3x squared times 4x squared, and that's going to give us 12x to the 4, with the idea being numbers go with numbers, letters go with letters. So the 3 times the 4 makes the 12, the x squared times the x squared makes the x to the 4. And once again, that's going to be the same with SURDS. Numbers go with numbers, SURDS go with SURDS. So for example, sorry, my pad has just frozen for a sec. We will be back in business in no time. There we go. So for example, if we have 2 root 3 times 4 root 5, that would be 8 root 15. Because numbers go with numbers, SURDS go with SURDS. Now, in many circumstances, the SURD will be able to simplify afterwards. Not in this case, but we're going to get to simplifying SURDS soon enough. So, let me also explain what a SURD actually is. A SURD is basically a number that has a square root on it that is not a squared number. So, for example, if we had, let me just delete all of this for us. If we had, I don't know, root 4, for example, root 4 in that form is a SURD, but actually root 4 equals 2. So that's an example of how we simplify SURD. But root 3, although root 3, if you type it into your calculator, you will get a number. It will be a very horrible number, but that's why we keep it in SURD form. So this is a sort of solid SURD. It cannot be simplified any further. So on that note, let's get into some simplifying SURDs. So I'll zoom back out for us. I will get the pen thickness back to normal, and we can start looking at this first question up here. Write root 48 in the form k root 3 where k is an integer. First of all, integer means whole number. So we want to write root 48 as a number times by root 3. And root 3 we know is a SURD, k is going to be an integer. So there's like a 4-step process to this. And if you follow this same 4-step process for any of these questions, you will always get it right. I think like I mentioned last time, maths is all about structure. I'm going to give you a structure right now. If you stick to it, you ain't going to get it wrong. So remember it. This is the process. We've got root 48. We want to split 48 into a product, meaning a multiplication between two numbers, one of which is a square number, and it has to be a square number, and you'll find out why in a second. So what is the biggest square number that goes into root 48? So the square numbers are of course 1, 4, 9, 16, 25, etc. 1 is no help to us. If we split this, if we use 1, then it's just 1 times 48, so 48 remains. 4 does go into 48, but it's actually not the biggest square number that goes into 48. The biggest square number is actually 16. So if we do, so we can write root 48 as root 16 times 3. Because 48 is 16 times 3, so hopefully you can see how we got from root 48 to root 16 times 3. This we can then split to root 16 times root 3, because the root of a product is the same as the product of two roots. And then root 16, here's the genius part, this is why it has to be a square number. Root 16 is 4. So we look at this and we say root 16 can be simplified, so we write it as 4. Root 3, can't do anything to it, so we just leave it as root 3. And that is the k root 3 situation, so k is 4 in this scenario. Let's try the next one. So what do you think? What is the biggest square number that goes into 50? Because it's saying write 50 in the form k root 2. So the biggest square number that goes into 50, obviously we're going to ignore 1 for the purposes of this topic. So 4, no, 9, no, 16, no, 25, yes, 25 goes in. Let's see if there's a bigger one. The next one is 36, that ain't going to go in. 49, that certainly isn't going to go in. So 25 goes into 50 two times, so we're going to write this as, so root 50 equals root 25 times 2, which is root 25 times root 2, which is, and root 25 goes to 5, not root 5, this is a mistake a lot of people make all the time. Root 25 is 5 root 2. That's the answer, simple as that. Now, this next question, we have an integer in front of the surd. Don't let what you don't know stop you from doing what you do know. We have a new element here, but we do know how to do the root 27. So we're just going to focus our attention on doing the root 27 first, because this question is 2 marks, and 1 mark will be for dealing with the 5, I'm sure, but we can still get 1 mark by just dealing with root 27. And this is a really important exam technique as well. A question is filled with lots of marks. You don't have to get the answer to get some of the marks. Just go for the first mark, then the second mark, then the third if there is, etc. So let's just focus on the root 27. So root 27 equals root 9 times 3 in this case. And we can also take a hint from the fact that the answer has a root 3 in it. So we know 3 is going to be one of the numbers that's divisible into this thing. So, we're going to write it as 9 times 3, which is root 9 times root 3, which is 3 root 3. Now that's root 27. We're dealing with 5 root 27, which means 5 times root 27. So what we're doing is 5 times 3 root 3. And if you remember from our sums with surds earlier, numbers go with numbers, surds go with surds. So we're going to times the numbers together to create 15. And because there is no surd on the 5, the root 3 just stays as a root 3. So 15 root 3. Okay. We do have another one here. Let's just do this one quickly because may as well. I'm going to actually incorporate the 7 into the full working for this one, so we just have an alternate view of how this one works. So this one will be 7 times root 20, which is 7 times root 4 times 5, which is 7 times root 4 times root 5, which is, and I'll do this on the next line, so we can see it all there, 7 times 2, root 4 is 2, times root 5, which is 14 root 5. So hopefully simplifying surds has become a lot easier for you now, because actually it's quite simple. As long as you know your square numbers, as long as you know your division, your multiplication, shouldn't be a problem. Okay, now we're doing getting a bit more integrated with the sums with surds. We're going to do some expanding brackets. Now you probably recognize this sort of setup of brackets from quadratics. So we're going to deal with it the same way. FOIL, F-O-I-L, is a technique that a lot of people learn. It stands for first, outer, inner, last, which is just in terms of the order in which we can multiply these. You can use that, it's great, but also you don't need to know that. Just make sure everything from the first bracket times is everything in the second bracket, and that should be fine. So here we do 2 times 2 is 4, 2 times negative root 3. Now when you have a number times a surd, we don't combine them into one number, we just shove them together, like 2 times x is just 2x. So 2 times negative root 3 is going to be negative 2 root 3. Root 3 times 2 is going to be positive 2 root 3. And then root 3 times negative root 3. Now because it's positive times negative, straight away we know it's going to be a negative. No worries about that. Root 3 times root 3, surds go with surds. Root 9 simplifies to 3. So remember, if you're timesing a surd by itself, essentially squaring a surd means like has a square root symbol on it. And if you square the square root, it just cancels out the square root. So it's a really, really important technique to remember. So root 3 times root 3 is 3. Root 5 times root 5 is 5. Root 10 times root 10 is 10. You can go the long route round here. Root 3 times root 3 is root 9, which is 3. Or you can develop this shortcut, which makes life a lot easier. And then we just collect like terms. So the 4 goes with the negative 3 to create 1. And the minus 2 root 3 plus 2 root 3 just cancels out. So the answer is actually just 1 with this one. Question 6. Anytime you see a bracket squared, you need to be so careful. I want you to remember this. I want this to pierce into your mind and burn on the skin of your brain. Your brain doesn't have skin, so ignore the fact that I said that. But burn into the muscle in your brain. When you see a bracket squared, write it out next to itself. Squared means times by itself. It doesn't mean square everything in this bracket. Now, I sound a little bit contradictory there because last week I said that we do square everything in our bracket when we're doing indices. However, that's different from if we have like 2ab squared, then we do square everything in the bracket. But this is now a sum in a bracket. So I'll clarify. Whenever you see a sum inside a bracket that's being squared, write the bracket out next to itself. So that means we're going to write this as 3 plus root 5 times 3 plus root 5. So we can do 3 times 3 is 9, 3 times root 5 is plus 3 root 5, root 5 times 3 is another plus 3 root 5, and root 5 times root 5 is root 25, which is 5. Then we collect like terms, 9 plus the 5 is 14, 3 root 5 plus 3 root 5 is 6 root 5. And that is it. And as we can see from the little bit up here, give your answer in the form a plus b root 5, where a and b are integers, whole numbers again. The a is obviously 14 and the b is obviously 6. So yeah, that's that one. Question 7 is basically the same thing, so I don't think we need to do that one. The same with question 8. All I would say is just be really, really careful about any negatives that are involved. Because yeah, double negatives, adding and subtracting negative numbers and multiplying them can be really tricky, so just be really careful with it. We're not going to focus too much on negatives today because we've got a lot to get through, but just be aware of this. Oh my god, question 9. This one, we have to do this one. This type of question catches people out so often. I'm going to skim through the first couple of steps pretty quickly because it's towards the end is where the mistakes always seem to happen. So 2 plus root 3 squared, so we're going to write that out like I said before, as a bracket next to itself. If my pen will start to work, which I'm sure it will in just a moment. There we go. So 2 plus root 3, 2 plus root 3, minus 2 minus root 3, 2 minus root 3. Okay, we can see all that on the screen. Excellent. So let's do a full expansion of this. 2 times 2 is 4, plus 2 root 3 plus 2 root 3 plus 3. So that's all of those things times together. Like I said, I'm doing it pretty quick. I'm going to keep this in a bracket for a moment and you'll see why. Take away, I'm going to do this in a bracket as well. 2 times 2, 4. 2 times minus root 3, minus 2 root 3, minus the same, minus 2 root 3. And then that times that. Negative root 3 times negative root 3 is positive 3. Now let's collect all the like terms within the respective brackets. So 4 and 3 make 7. 2 root 3 plus 2 root 3 is 4 root 3. Minus 4 times 3 is also 7. And minus 2 root 3 minus 2 root 3 is minus 4 root 3. So really be really careful about that. When we're minusing a negative from a negative, the idea here is we're starting at minus 2 root 3. So we're starting all the way down here on the negative side of things, and we're taking away another 2. So we're going further down, we're going even lower down. Now here's the bit where people fuck up all the time. The negative, the sign in between them, this here, that means we're minusing the entire second sum. This is where the brackets are really important. So it's going to be 7 minus 7. I put that dot there, it's going to make it look like a divide, but it is not. 7 minus 7 cancels out. 4 root 3 minus 4 root 3 actually means plus. So that is going to give us a final answer of 8 root 3. So the moral of this story is, whenever there is a sum minus another bracketed sum, keep the brackets involved because you're going to minus everything on that side. So we are minusing 7 and we are minusing minus 4 root 3. Don't fuck it up. I mean, you will, and that's fine, but don't fuck it up in your exam, fuck it up in your practice, and then learn from it. Rationalizing the denominator. Okay, this is a new aspect of SURDS, a really important one. First of all, let's quickly discuss what rational and irrational actually means. So a rational number is a number we can express as a fraction of two integers. So a number over a number. An irrational number is a non-recurring, never-ending decimal. Now I'll say that again. An irrational number is a non-recurring, never-ending decimal. For example, pi. Pi doesn't recur, none of the letters repeat over and over again. It is never-ending. We don't know the next value of pi. We know it's at some sort of hundreds, maybe even thousands decimal places, but we'll never know the end because there is no end. It goes on infinitely. And we can't write pi as a fraction of a number over a number, an integer over an integer, I should say. Surds of non-square numbers, such as root 3, are also irrational. Root 4 is not irrational because root 4 is 2. But root 3, root 5, root 6, root 7, root 8, anything that's not a square number, they are irrational. We do not like irrational numbers on denominators. Oh, no, we don't. So we want to rationalize the denominator, make the denominator rational. It's okay if the numerator is irrational, we don't give a shit about that. There's actually a really, really simple technique. This is one of the genius elements of GCSE maths. Whoever came up with this, I want to find out, I'm sure it will take a quick Google search, but whoever came up with this method, I think is just a genius. I think everybody who comes up with most math stuff are genius anyway. But this one is because it's so simple. The way we rationalize the denominator is we times the top and bottom by the denominator. So we're going to times 6 over root 3 by root 3 over root 3. Now this is going to change the way it looks, but it's not going to change the value because root 3 over root 3 equals 1. When you have a number that's over itself, it just equals 1. 5 over 5 is 1, 10 over 10 is 1. Root 3 over root 3 is 1. So the value, we are only timesing this fraction by 1. So it stays the same value. So 6 times root 3 over root 3 times root 3, that's going to give us 6 root 3. Remember, when we have a number times a surd, we just shove them together. And then root 3 times root 3, as we know, because they're two surds, we combine them into one number, which creates root 9, which is 3. And then same with division. Numbers go with numbers, surds go with surds, so we can divide these numbers by each other. 6 over root 3 creates just 2, and root 3, the surd is not divided by another surd, so it just stays out of root 3. 2 root 3. That is the simplest form of rationalizing the denominator. So remember, you times the top and bottom by the denominator. This next question. Now, things always look more complicated when algebra is involved, but in fact the method is exactly the same, and that's the beauty about learning the structure of maths. The structure is always the same no matter what values they throw at us. So we are still, once again, going to times the top and bottom by the denominator. So we times the top by root x, and we times the bottom by root x. X times root x is just x root x. Don't be afraid to shove stuff together even in algebra. If you're unsure, imagine x is a number, call it 5 or something. 5 times root 5 is 5 root 5. And then root x times root x is just x. And then the x's cancel out because numbers go with numbers. And in this case, x would be a number. So the answer is just root x. Beautiful. Rationalize the denominator. Things don't change when there's a sum on top. It's still exactly the same. We're going to times the top by root 2, and we're going to times the bottom by root 2. What we're going to be careful of here is making sure we times the entire top by root 2. So I like to put a bracket around it like that. So that means we're going to do 1 times root 2 is just root 2, plus root 5 times root 2 is root 10. Over root 2 times root 2 is 2. And, well, that's the answer. We can't simplify any of those surds because no square number goes into them. Remember, that's how we simplify surds, by finding what the biggest square number that goes into them is. So we're happy just leaving it like this. A lot of people might look at this and say, oh, we can divide everything by 2. No, don't you dare. Surds are only divisible by surds. If you try and divide root 2 by 2, you fucked up. I'm sorry, mate. Alright? It's done. Only divide a surd by a surd, only divide a number by a number. We cannot simplify this any further. I'd like to think this one is doable for you now, because it's basically exactly the same as this one. So we'll skip that one. Although actually, no, we're going to do this one because there is a lot of simplification we can do that we couldn't do in this one. So let's scroll back down. Come on, mate. What's happening here? Oh, there we go. So what do we do here? We times the top and bottom by the denominator. So we're going to times by root 3 and times by root 3. 3 times root 3 is 3 root 3. Root 6 times root 3, this is going to get good, is root 18. Now some people may have realized root 18, square number goes into 18. We will circle back to that, don't you worry. Over root 3 times root 3 is 3. 3 times root 3 is root 9, which is 3. Now, this question, also a good thing to note, is in exam questions, they always give us enough information, of course, through the question, but they often always hint at how to do things. This question doesn't say rationalize the denominator. This question above did. This one doesn't. This one says simplify. Now, I wonder why this one says simplify. Maybe it's because we need to simplify. So that's the hint to us that it's not simply rationalizing the denominator question, it is a simplification question as well. So always read the question very carefully and always be aware of the wording that they use. So if we simplify this, so root 18, if we take root 18 to one side, so let's do that over here. So root 18, 9 goes into that. So we'll write that as root 9 times 2, which is root 9 times root 2, which is 3 root 2. Go back to our question. 3 root 3 plus, now we know to be 3 root 2 over 3. Every value here has a 3 in it. Not a root 3, a 3, which means we can divide things here. That has a 3, that has a 3, that has a 3. So the answer is root 3 plus root 2. We can only cancel out stuff on fractions if every individual is divisible by the same thing. So that's why it works here. This next question looks horrendous. I'll put my hands up and say that looks horrible. But actually what's going to happen here is a lot of stuff is going to cancel out. And that's why it says here simplify fully. So not only simplify fully. That's letting us know there's some simplification going on, but there's more than just one step of simplification. You must show all your working. I mean, that just is what it is. Just make sure you show all your fucking working. We will do this one because I think it's valuable. But the first thing I do here, and this goes for when we have just algebra, when we're solving algebra, when we're expanding brackets, etc. Simplify everything that's in its place first, if possible, before combining it with other things. What I mean by that is on this numerator here, a lot of people, because we're in this structure of times at top and bottom by the denominator, may go straight to timesing by root 11 on the top and timesing by root 11 on the bottom. While that is mathematically the correct thing to do, we don't want to do that just yet, because we can actually simplify the numerator first. So just be aware of that. If you can simplify something before doing a more elaborate step, then do it. So let's times out this bracket on top. So 4 times 4 is 16. 4 times minus 2 root 3. This is a little bit complicated now. So the number goes with the number. So we know it's going to be a negative because it's positive times negative. So minus 8 root 3. 2 root 3 times 4 is plus 8 root 3. And 2 root 3 times negative 2 root 3. Be really careful about this. It's going to be negative because it's positive times negative. 4 from the 2 times 2. And a 3 from the root 3 times root 3. So 4, 3, 12. Now I'll actually do that in a slightly step-by-step way because I jumped it there. But so it's a negative, I'll do it up here. The 2 times the 2 makes a 4, and the root 3 times the root 3 makes a positive 3. So we times those to get the negative 12. That's how that works. And then a lot of this stuff cancels out. The minus a root 3 and the plus a root 3, they fuck off. 16 take away 12 is just 4. The numerator is just 4 over root 11, which I think you'll agree is a much simpler equation or rationalizing of the denominator to do than what we were originally given. So this is just going to be times root 11 on top and bottom, so 4 root 11 over 11. Simple as that. Okay. Alright, now we're getting serious. What the fuck is this? So, this is where we have a sum on the denominator. Now when we have a sum on the denominator, it doesn't change too much, but there's one element we need to be really, really aware of. We're still going to times the top and bottom by the denominator, but we're going to flip the sign when we multiply. And you will see the genius reason why this works later on. So we're going to do 5 plus 2 root 3 over 2 plus root 3 times 2 minus root 3 over 2 minus root 3. Now, you may be looking at this and say, why the hell are we flipping this sign? What is the point? You will see very soon. This is genius. This is one of the reasons I love this topic. So I would advise putting brackets around these because we're going to times all of this and it's everything times everything. So just putting the brackets gives us that sort of visual help that, what we're doing is going to be the big expansion. So 5 times 2 is 10. 5 times minus root 3 is minus 5 root 3. 2 root 3 times 2 is going to be positive 4 root 3. And 2 root 3 times negative root 3 is going to be negative 2 times 3, so 6. The 2 obviously being from just the 2 and the 3 coming from the root 3 times root 3. Over 2 times 2 is 4. 2 times negative root 3 is minus 2 root 3. Root 3 times 2 is positive 2 root 3. And root 3 times negative root 3 is going to be negative 3. On the numerator, 10 take away 6 is 4. Negative 5 root 3 plus 4 root 3 is negative root 3. And this is the genius part. Because we flipped the sign, that created a negative 2 root 3 and a positive 2 root 3, which cancel each other out, therefore getting rid of any irrational values, leaving us just with the 4 take away 3, which is 1. And as we should know, when anything is over 1, when any fraction is over 1, it's just the numerator. 4 minus root 3 over 1 is just 4 minus root 3, which is what we want. So also, when a question says, show that this is this, and it tells you the answer, that's great because you know if you've got it right or not. And the fact that we've got to 4 minus root 3 means we know 100% we've got it correct. And if you don't get what they're asking for in the question, then although that sucked, at least you know you've made a mistake, and that gives you the power to go back and check, try and find your mistake, knowing that there must be one in there. So, I won't do, we'll do one of these because they get a bit, that's fine. So this one we'll skip because it's basically identical to the other one. There's just going to be a lot of simplification in that one because there's so many 3's that inevitably stuff's going to be divisible. We will do one of these two. Which one should we do? Let's do this one because the answer seems to simplify a bit more. Okay, this is horrible. This is probably like one of those questions you get right at the end of the paper. How many marks are they saying this one is worth? 3 marks, is that it? Okay, fine. Well, still worth doing. And this is the thing about those questions at the end of the paper. Majority of people are not going to get those right. That's the first thing you need to just accept. Grade boundaries are so low nowadays that even just a couple of years ago, if you got 50%, that's a 7. 50% is a 7, are you kidding me? It's gone slightly higher nowadays, of course, but that's reflected by the idea that those last few questions, 4 or 5 questions that are 5 marks, some even 6 marks, majority of people aren't going to get them. So if you're aiming for sort of 6 or 5, 6, 7 region, if you can just try and pick up a couple of marks in each of those questions, it makes the world of difference. And I'm going to show you how to do that. Maybe not just in this question, but over the course of time. So what we do here, and this is just a particular trick for this type of question, what we're going to do is we're just going to focus our attention on the denominator, because that's the horrible bit right now. The 2 on the numerator is fine. We know how to deal with that later on. This denominator is what's horrible. What we look and see is that we actually have a sum here, a fraction, add a number. So what I would do, what would I do here? Actually, no, I'm going to teach you the super shortcut way. We are going to times the top and bottom by root 3. Now, usually in rationalizing the denominator, as I've said, we times the top and bottom by the denominator. We're not going to do that here because this denominator is fucked up. So what we're going to do is just times by root 3, and I'll show you why. You do have to be really careful about your multiplication here. So 2 times root 3 on the top gives us 2 root 3. And now, timesing everything on the bottom by root 3, so if you times 1 over root 3 by root 3, that creates root 3 over root 3. Because when you times a fraction by a number, the number just times this to the top of the fraction. So if we times this fraction by root 3, it creates root 3 over root 3, which is just 1. Then we times the 1 by root 3, and that is just plus root 3. And in that one single step, we have completely simplified this fraction into a form that is not easy, but is much easier. So that would be the case if I scroll up to this one, times this one on the top and bottom by root 2. And the same thing will happen. This will just turn into a 1, and this will turn into a 2. Which actually is super easy. 1 plus 2 is 3, and the numerator gets times by root 2. So that's actually the quickest question in the world. We could have done that as well, but it's fine. And now we just do a regular rationalizing denominator, times by 1 minus root 3. Remember, it's timesing by the negative, 1 minus root 3. Put brackets around everything. I just would, it's just helpful. And then, look, actually, no, let's do it. No point skipping corners for the sake of a few seconds. So times that by that, we get 2 root 3. Times that by that, we get minus 2 times 3 is 6 over 1 minus root 3 plus root 3 minus 3. Those are going to cancel beautifully. Then we got 2 root 3 minus 6 over 1 minus 3 is minus 2. So we're going to divide everything by minus 2. Actually, let's just divide everything by 2 to start with. We'll deal with the negative bit afterwards. Because everything is divisible by 2 here, that disappears, that turns to a 3, and that turns to a 1. So when something is over minus 1, numerically it stays the same, because dividing by 1 doesn't change anything. Dividing by minus 1 just flips the signs. So that creates a positive 3 and a minus root 3, which is what they have there. Okay. So we're going to move on now. There's a couple more questions on SURDS, but actually these are the same things of what we've done previously, just with letters instead of numbers. So as long as you just stay strong with looking at those letters and thinking a times a is a squared, I don't need to worry about that shit, root b times root b times root b is b, then we're good. We're going to move on to functions now. Functions is another topic which a lot of people don't like. And I can understand why. It's a little bit confusing, but I'm going to simplify everything for you, at least I hope to. We're going to start from the beginnings of functions. Functions is essentially substitution, essentially algebraic substitution. And actually it's very just intuitive in this sense. So for example, given that f of x equals x minus 4, find f of 5. Well, what's changed from here to here is that the x has become a 5. So on the right hand side, the x should also become a 5. They are quite literally changing the x to a 5, so we also change the x to a 5. We're just following their lead, which means it's going to be 5 minus 4, which equals 1. That's it. And so for the second one, we go back to the original question, f of x equals x minus 4, so f of 3 equals 3 minus 4, which equals negative 1. So the basics of functions is really, really simple. It's just algebraic substitution. Let's try it for these ones. So g of x is 2x squared minus 10. So g of 2, we just swap out the x for a 2. And when we're doing substitution, I would always advise to do it in brackets, put the substitution in brackets. So 2, frozen again, I'm sure we'll be back in a second. There we go. 2 brackets 2, that's the substitution that we're putting in, squared minus 10. Bit maths, we do the 2 squared first to create 4, times that by 2 to create 8. 8 minus 10 equals minus 2. For the next one, it's going to be the similar thing, 2 and minus 2 squared, take away 10. Now, this is where we've got to be careful. Minus 2 squared is positive 4, remember that? Times by the 2 is 8, take away 10, also gives us minus 2. So it's a really interesting question on how, given a different number, a positive and a negative, comes out with the same answer because it's been squared. This one's slightly different, but intuitive once again, in the sense that solve g of x equals 8. Well, they've told us at the top, g of x equals 2x squared minus 10. G of x now equals 8, which means 2x squared minus 10 equals 8. Now pay attention to that, because a lot of people lose some silly marks on that on what is a very, very simple question. G of x is 2x squared minus 10. G of x is 8. So 2x squared minus 10 is 8. And the word is, when we use it in language, when that converts to mathematics, is an equals. Is means equals. And then we're just solving this relatively simple algebraic equation where we want to make x a subject. So we're going to add 10 to the other side to get 2x squared equals 18. Divide both sides by 2 to get x squared equals 9. And then square root both sides to get x equals positive or negative 3. Remember, any number, when it's squared, has 2 square roots, positive and a negative. I'm pretty sure, actually I don't know whether you'd get all the marks if you just put positive 3. You probably would, but better to be on the safe side and put plus or minus. That's going to be the same for these ones, so I don't think we need to do these questions. Same for these ones as well, except for part C where we're dipping into the inverse function side of things. Now, shall we do some inverse functions first? Yeah, let's do inverse functions first, because I think they're actually a lot simpler than than the composite functions, which we're going to get to later, although some people would argue with me on that one. So, inverse function. Inverse basically means reverse, doing the reverse of something. So, I don't want to start with this question actually, because I think we can find a better one. Yeah, let's go for this one here. So, ignore 5a, we're just going to jump straight to 5b on this case. Work out an expression for f to the minus 1 of x. So, that means the inverse of x. What we're going to do here is we're going to use y. We're going to say y equals 2x minus 4. And we're going to use this y to help us reverse everything, and we're going to get rid of the y. Basically use and abuse it. So we use the y to make x a subject now. And again, this is just a process, just a standard structure of finding the inverse. If you just remember that this is the formula, the format of how to do it, then anything they throw at you, as long as you're decent enough at algebra, you'll be able to solve. Y equals 2x minus 4, let's make x a subject. So we're going to add 4 and divide by 2. So it's going to be y plus 4 over 2 equals x. Then, like I said, we're going to use and abuse this y. This is the answer, but we don't want a y in it, we want an x in it. So the inverse is actually going to be x plus 4 over 2. So remember that. We make y equal to the equation, use the y to flip everything over to the other side to make x a subject, then swap the x and the y and get rid of the y. We don't want it anymore. X plus 4 over 2 is an expression for f to the minus 1, aka inverse f of x. So if we take that to go back to this one here, this is basically saying find the inverse, then make it equal to 8 and solve it. So quite a few steps in this one. So let's first of all find the inverse function of f. So remember, we're going to make y equal x squared minus 3. We're going to make x a subject, so y plus 3 equals x squared. So the square root of y plus 3 equals x. Then we swap the x and the y to get root x plus 3 is our inverse function, and that equals 8. So we've done quite a hefty chunk in just these 4 steps. We found the inverse of f of x, and now we've made it equal to 8. And now we're going to solve this. How do we solve x? Well, by making it the subject. So we're going to square both sides. X plus 3 equals 64. And then we're going to minus 3 from both sides. X equals 61. And that's it. So, and I'm going through this pretty quickly, but don't forget, you can always come back and look at these videos. They're going to be available on examriz.com for a certain amount of time. So I'm going quickly so I can get through a lot of content, but feel free to check the video out afterwards and go through it, pause it, slow it down, review it again, because it's really, really valuable stuff, if I do say so myself. We're going to skip past these and just stick with the inverse functions for the time being, because I think that's going to be what's most valuable to us here. And then we'll come back and do the composite functions. Okay, here we go. Here's a nice full question for us where we're finding both the inverses and then do an equation between them. So, work out an expression for g to the minus 1x, so inverse g of x. This one is a nice simple one. G of x is just x plus 3. So we do y equals x plus 3, make x a subject, y minus 3 equals x. So the inverse function is x minus 3. Work out an expression for inverse f, y equals x squared minus 17. Whoa, that is the worst 17 I've possibly ever done. So we're going to definitely delete that. Minus, I'm going to get a pen back. There we go, minus, come on, pen. There we go. That's a decent 7, but there's a 17. Okay, x squared minus 17, and we're going to make x a subject here. Add 17 square root to give us y plus 17 square rooted. Got a bit of a lag situation going on with this pen. Don't you worry, we'll be back with it in just a moment. There we go. I think it needed to crash just so we could reload it. Bear with me for just a second. If you do have any comments, by the way, anything you want to say, give any encouragement, or let me know how fantastically I'm doing or how fantastically you're doing, please do let me know. Okay, so like I said, we're going to make x a subject by adding 17. So y plus 17 equals x squared. Square root both sides, and that is the square root of y plus 17 equals x. So the inverse function of f is going to be square root of x plus 17. Don't forget to swap out the x and the y at the end, because a lot of times you could look at that and you think, hold on, what the hell's going on? Why have I got a y here? Just remember, we're using and abusing that y. Get rid. And then we move to part C. Solve f inverse equals g inverse. Now this doesn't need to be complicated in any sense. We found inverse f, we found inverse g. It's telling us to put an equals between them, so that's quite simply what we do. Square root x plus 17 equals x minus 3. So this now really is no longer a functions question, if we're being honest. The functions have been done. This is now algebra, solving algebra. And the way we do that is by grouping the x's together. But this is a little bit of a tricky one. I'm not surprised this one is 4 marks, because it's a bit tricky, but while we're here we may as well do it. First thing we want to do is get rid of the square root, because I look at a square root like an umbrella that's sort of blocking any movement from this x or the 17 to move to the other side. So we need to get rid of that barrier, that roof over the sun, to be able to start moving stuff around. So we're going to square both sides. We square the left hand side, it just gets rid of the square root, which is nice. Squaring the right hand side is going to be x plus 3 squared, and remember what I said about a sum squared right in next to itself. So that's going to be x minus 3 times x minus 3. And we're going to fully expand that. Left hand side stays root 17, right hand side is x squared minus, I'm doing this quite quickly, I'm going to skip a step, minus 6x plus 9. That's from the negative root 3, negative root 3. Creates a negative, not root 3, God, my head is stuck in surds. Negative 3x creates a negative 6x. Now, at this stage, we should spot that this is starting to look like a quadratic. A quadratic, for those who don't know, is when we have the x squared, x, and a number form. And when we see a quadratic, we're going to start treating it like a quadratic, which is move everything to one side. So as soon as you spot that it's looking like quadratic, treat it like quadratic, move everything to one side. So we're going to minus the x, and we're going to minus the 17, which is going to give us x squared minus 7x minus 8 equals 0. And once we have everything on one side equaling 0, we're going to factorize a quadratic. double bracket factorization. We're going to do two numbers at times together to make 8 and add or subtract to make -7. First number is going to go x and x, and obviously this is going to be 1 and 8. 1 and 8 times to make 8 and add or subtract to make -7. What combination of 1 and 8 makes -7? -8 plus 1. And then of course, for this equation, for this bracket times under bracket to equal 0, we're going to need to make the individual brackets equal 0. So x minus 8 equals 0, so x equals 8 by moving that to the other side. And x plus 1 equals 0, so x equals -1. So that was a very quick sort of lesson on quadratics there. But when you've simplified the brackets and it equals 0, set each bracket to equal 0 to work out what the x value actually is. Okay, so that's inverse functions for you. I hope that was enough practice. Maybe if we have time at the end, we will spend some time going over that again. I think we are just past the halfway stage, so we're going to take a little break, just 5-6 minutes, so I can have a glass of water and stretch my legs a bit. And I suggest you do the same. Go hydrate, stretch your legs, get the blood pumping so we can come back refreshed, re-energized, and ready to do some composite functions. Okay, I will see you in 5. Hello, welcome back. Hope you had a good break. I do hope you stretch your legs. I do hope you hydrated. I did myself. Don't underestimate the importance of getting the blood pumping through your body, staying hydrated, staying fueled. I've made it a regular part of my routine to go on long walks now between sessions. First thing in the morning, maybe have a quick jog. It's a good way to start the day. I'll be honest with you, I don't manage to do it every day. Sometimes I give myself a morning off, have a bit of a lie-in. But the power of exercise on your brain is quite incredible. And over Christmas, over holidays, anytime when you're revising, exercise is such a powerful tool. So yeah, I think even just taking 5-minute breaks in between study sessions, walk around, climb the stairs. If you have stairs in your house, go up and down stairs a few times. It really does make a difference. Thank you for sticking with us. Thank you for coming and learning on your Christmas Eve. I think I've mentioned it before, but doing something like this allows you, in my opinion, or allows me, or did allow me back in the day, to enjoy my Christmas Day and Boxing Day guilt-free, because I knew that I put in the hours before, and I know I will put in the hours after as well. Okay, let's get back to the maths, because after all, that's what we're here for, aside from my just great banter. And let's get back with some composite functions, because composite functions, I actually really like them. A lot of people don't, I do. And I think that might be because I've got a pretty good way of dealing with them. So here we have first of all, let's identify a composite function. It's when we have these sort of two letters put together. We have f of x is this, g of x is this, gf3. This is a composite function because we are combining the functions. The way we do that is, what I would advise is put an extra little bracket around here. I'm going to make my pen a little narrower so we can be a bit clearer about that. Put a little bracket around those to separate the idea of gf3 as actually g of f of 3. Now, visually we can now see that this f of 3, well, that's just what we were doing before. Let's find f of 3, which is going to be 2 brackets 3 minus 4. So 2 times 3 is 6, take away 4 is 2. So we know f of 3 is 2. Now f of 3 is 2, meaning g of f of 3 is actually g of 2. And then we just plug 2 into the g function. So it's going to be 3 brackets 2 plus 5. 3 times 2, there's no need for that extra bracket there. 3 times 2 is 6 plus 5 is 11. So putting that bracket to separate the letters is such a powerful tool because it just creates two simple algebraic substitutions. I'm going to see, because I'm going to zoom in actually and going to create one of my own questions on this topic because I think it's a really, really important one to do. Let's say f of x equals 4x minus 3 and g of x equals 2x squared. Let's say find fg minus 1. So what we would do is we'll put a bracket around that, and first we'll just find g of minus 1. So g of minus 1, we plug it into here, and that's going to be 2 times minus 1 squared. Big maths means we do the indice first. Minus 1 squared is positive 1 times by 2 equals 2. So g of minus 1 equals 2. That means when we write this function up here, f of g minus 1, no, f of 2, because g minus 1 is 2. So f of 2, then we scroll back up to here. 4 brackets 2 minus 3 is what we're going to be doing. 4 brackets 2 minus 3. 4 times 2 is 8 minus 3 is 5. So that's how we deal with composite functions in the sense of when we have a number there instead of an x. Just substitute into the first one, get that answer, then sub into the second one. Merry Christmas to you as well, Lily Marotti. I hope I pronounced that right in one of the two ways I did it. I hope you're all having a wonderful Christmas. Song Kim, thanks for joining us again. I'm going to be from last week. Merry Christmas, face blue, wide eyes. Don't know what that means, but I tend to agree. Let's scroll down to some more complex composite functions. That's what we got here. Okay, we're going to get serious now. Given that f of x equals 3x plus 1, g of x equals x squared, find f gx. Now, I'm going to put the extra bracket around here, like we're used to doing. That's pretty thick pen. So let's do that. Okay, so g of x is x squared. Now, before we would find out what that value was, then we would plug it into the other one. There is no value here, it's just an x, it's in terms of x. But the fundamental idea stays the same. We're going to take the entire function of g of x and plug it into the f function. So g of x is x squared, so we're going to plug x squared into the f function, which is going to be 3x squared instead of x plus 1. Now think about it. If we had a value for g of x, if it was 3, for example, we would plug 3 in for x here. But it's not, it's x squared. So we plug x squared in for x. That's why there is just a straight swap. X is x squared, because we're plugging the x squared into there. Now I understand if this is a little bit complicated at first, but bear with me, we're going to do a couple of examples, and hopefully as we go through it, it'll start to make a bit more sense, and then you can come back to look at this question and see, oh, I see what he means. So, let's go to the next one. Work out an expression for gfx. This is where just the two values have been swapped around. So gfx, we're going to take the entire f of x function and plug that into the g function. So the entire f of x function, I will just remove that so you can see it clearly. The entire f of x function is 3x plus 1. So 3x plus 1 is going to be subbed into g of x. So instead of, and when I say that, it's instead of typing x, or instead of writing x, I should say, as soon as you go to write x, write what we're subbing in instead. So here we would be writing for g of x, x squared. Instead we're going to be writing 3x plus 1 squared. What the hell is that 1? Actually, you can tell it's a 1, it's fine. So that's the expression. Yeah, so we're taking the entire f of x function, 3x plus 1, plugging it into the g of x, which is x squared, so it's going to be the f of x function squared. And the final step is solve f of x, solve f gx equals g of x. We just make this equal to this. That's going to end up in being a quadratic again. We won't focus on that just now because I do want to get through as much of the function stuff as we can. But But yeah, I hope that makes sense. Let's find the net composite function. If there isn't one, I will make one up for us. There is not. So I'm going to make one up. So let's just zoom into this blank space here. Okay. Let's say f of x equals 4x plus 5. Actually, no, let's not say that because those are some big numbers and I think I know where this is going to go. Let's say 2x minus 1. And let's say g of x equals, I'm going to make it a little bit complicated so we sort of cover all bases here, 2x squared minus 5. So let's say we're doing g f x here. So g f x, pay attention here, it's really, really careful. It's really important, we have to be careful rather. Put the brackets around f of x so we can see clearly that we're taking f of x in its entirety and we're going to put that into the g function. So f of x is 2x minus 1. That is going to go into the x value there. So we're going to write out g of x, but as soon as we get to the x, we're going to write 2x minus 1 instead. There's going to be 2 brackets 2x minus 1 squared minus 5. Now if you can see visually, the x that was in g of x has been entirely replaced by the 2x minus 1. That is what is happening here. We are substituting an equation into an x value. Then in my question, I'm going to say simplify. So we're going to expand and simplify this. So BIDMAS comes first. So we're going to do the indice first. So we're going to square this bracket. Now remember, whenever I said earlier today, when you have a bracket squared, write the bracket next to itself. So that's going to be 2x minus 1 times 2x minus 1. Fully expanded, that's going to be 4x squared minus 4x plus 1. I skipped a couple of steps there, but if you fully expand that, this is what you get. So that is just in place of this bit here. So that's now going to be 2 brackets, 4x squared minus 4x plus 1, take away 5. And then we're going to multiply out the brackets, so that's going to create 8x squared minus 8x plus 2, then minus 5, and then we just collect the like terms at the end to create 8x squared minus 8x minus 3. So we do not ignore the fact that there is a 2 happening here and a minus 5 happening as well. It's a lot going on, and that's why this question, in my opinion, would be worth probably 4 marks. So yeah, that's composite functions. Like I said, these videos will be available on the ExamRiz website afterwards for a certain amount of time. So do feel free to go back, have a look through them again, pause them on these moments, and review the questions. And of course, if you have any issues, the ExamRiz platform will be available in the future to go through detailed content as well. It's not just going to be live sessions, we're going to have actual content videos as well, so that you can watch at any time. So that's inverse composite functions. Let's see if there are any slightly different questions. This one, actually, let's do this one. I'm going to delete the sum we just did, as beautiful as it was, so we can practice this question here. A function f is defined such that f of x equals x squared minus 1. Find an expression for f of x minus 2. This looks a lot more complicated than it actually is. It's actually really, really simple. Remember earlier we were doing like f of 3 or f of 5. We just replaced the x with whatever number they had replaced x with. Well, right now they're replacing x with an x minus 2. So we're just going to write out the right-hand side. Instead of x, we're going to put x minus 2. So this is going to be x minus 2 squared minus 1. Then we just expand the bracket and simplify. So expanding this bracket, remember, times out the bracket, write it next to itself. X squared minus 4x plus 4 minus 1, that should be. So again, I've skipped a couple of steps in the expansion of that bracket, but you don't skip steps, right? I can skip steps, but you can't. X squared minus 4x plus 3 will be the expression. And then part B is hence solve that equals 0. So quite simply, we've found f of x minus 2. It's now saying f of x minus 2 equals 0, so we make what we found equal to 0. X squared minus 4x plus 3 equals 0, and this is just standard quadratic factorization. Should be second nature to us, to be honest with you. If it's not, then let us know and we can perhaps do a section on quadratics. So what times it together to make 3, or adds or subtracts, and adds or subtracts to make negative 4? It's going to be 3 and 1. Obviously there's only one pair of numbers that times together to make 3. 3 and 1. So it's going to have to be 3 and 1. What combination of 3 and 1 makes minus 4? It's going to be minus 3, take away 1. So you're starting at minus 3 and you're going even further down. And then to find out what x actually equals, to solve it, you make each individual bracket equal to 0. X minus 3 equals 0. X equals 3. X minus 1 equals 0. X equals 1. Okay, and let's round off functions by doing an inverse function, just to jog our memories from before the break. Let's see how much you remember from just 15 minutes ago. Function f is defined such that f of x equals 4x minus 1. Find the inverse. Remember what the first step we do is? Make y equal to the equation. Y equals 4x minus 1. Then we make x a subject. What the hell did I do there? That's a wiggly y. That's fine. That's alright, it's got character, that y. Y plus 1 equals 4x, and then y plus 1 over 4 equals x. So our inverse function is going to be x plus 1 over 4. Okay, we will finish there on functions, because next up, what have we got? We've got some vectors. Now, vectors come in 2 levels of difficulty. We're going to go through the easier ones first, and then I'm not sure we'll get enough time to go through the more complex ones, so maybe we'll get onto that next week. We will be having another session next Saturday. Not sure of the exact time yet, so keep your eyes peeled on my TikTok and the Examriz social media pages as well. Okay, let's start on vectors. A equals 2, 3, B equals 1, 5. What the hell does that mean? So vectors are basically measuring magnitude and direction. Magnitude means size, and direction means, well, hopefully you know what direction means. For those who, I very much enjoy this. Have you seen the film Despicable Me? I'm sure you have. Who hasn't seen the film Despicable Me? So the bad guy in Despicable Me is called Vector, and he describes himself as having magnitude and direction. Remember that scene when they're in the bank and they're waiting to go in, Vector's showing off about all his powers, magnitude and direction. That is what a vector is. That's why he calls himself Vector. I think that's brilliant, genius writing. Anytime a film involves maths in its writing, and its jokes especially, I'm in. You've got me. You've nailed it. So vector is magnitude and direction. A equals 2, 3. What that means is A goes 2 to the right and 3 up. B is 1, 5, so that means B goes 1 to the right and 5, why don't I do that? 5 up. So A is a line that sort of goes in that direction, and B is a line that goes in a much steeper direction. We don't really need to know that for this first bit though, because this is actually super simple. Write as a column vector A plus B. Quite simply, we're just going to add the top numbers and add the bottom numbers. So that's going to create 3, 8. Literally as simple as that. Just to clarify once more in terms of this, the top number represents the x direction and the bottom number represents the y direction. Much in the same way as coordinates. The first number is the x, the second number is the y. In vector, the top number is the x, the bottom number is the y. And because it's a positive number, that means it's going to the right. If it was a negative number, it would be going to the left or going down if it was a y. The second one, 2a plus 3b, well, quite simply, we times the a vector by 2, we times the b vector by 3, and then we add them. So timesing the a vector by 2 creates 4, 6, and then timesing the b vector by 3 creates 3, 15, and then we add those together to get, quite simply, 7, 21, which is very simple. Vector C is drawn on the grid from point P draw the vector 4c? Well, quite simply, it's just c 4 times as long. So as we can see, c goes 2 across 1 up, times that by 4 means it's going to go 8 across 4 up. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. And of course, we would be using a ruler in real life with this. So we would do that straight line. That's a pretty straight. I'm pretty pleased with that actually. I'm pretty glad I did not use a ruler because then we wouldn't have been able to see how skilled I am at drawing that line. So that is the vector 4c. This is exactly the same thing, so there's no point doing this. But yeah, we just add the top plus top, bottom times bottom. Remember, A, 4, 1 means 4 to the right, 1 up. This one will mean 3 to the right, 2 up. For this one, actually, we will do this. So C is 5 minus 4. From point P, draw the vector C. That means 5 to the right and 4 down, because it's negative 4. So it'll be 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's see if I can do a straight line as good as the last one. This one's going to be more difficult because it's going downwards. That's often more difficult to draw, but let's see. Not too bad, not too bad. That is the vector C though. We don't need to do this, but then part B, translate the vector. So when we are translating the triangle by this vector, that means we're just moving the entire thing. So I would just go step by step with each corner. So this corner here is going to 3 to the right, 2 down. So 1, 2, 3, 1, 2. That corner is going to go there. This corner here is going to go 1, 2, 3, 1, 2, there. And this corner here is going to go 1, 2, 3, 1, 2. So the triangle is going to end up like that. Okay. Now we're getting into some vector mathematics. A is the point 32, B is the point 41. So these are now coordinates. Right now, because the numbers are written next to each other, that's not a vector. That is a coordinate, which we should be very familiar with. Write as a column vector AB. What this means, the column vectors are what we've been doing, the number on top of the other one, where the top one is the x direction, the bottom is the y direction. Write as column vector A to B. This means how do we get from point A to point B? That's what that arrow on the top means. AB is how do you get from A to B. A couple of ways of doing this. First of all, you could do it quite simply in terms of looking at point A and counting how far across it takes to get to point B. So in this particular case, the x direction, we're going from 3 to 4, so that's just an increase of 1 in the x direction. And the y direction, we're going from 2 to minus 1, so we're going down by 3, which is that. So you could do it that way, but maybe sometimes that could be a little bit complicated, or just you don't prefer it. So what I'm going to do is I'm going to tell you the alternate version, the more mathematical, formulaic way of doing it. And that is vector AB. I'll just delete that. So this is basically a formula. Vector AB equals B minus A. So we minus the coordinates from each other. So 4 take away 3 is 1. Minus 1 take away 2 is minus 3. So if you prefer memorizing a formula, you can do that. AB equals B minus A. The same way in this one, CD equals D minus C. Or, like I said, you can do the option of just counting how many do I need to go up or down to get from this one to this one. It's entirely up to you. I'm just giving you the tools. You can decide which tools you want to use. So this one, D minus C, so 2 take away 5 is minus 3, and 1 take away minus 2, take away minus makes a plus, so 1 plus 2 is 3. And that's the answer for that one. We can skip past these ones because they're exactly the same. Just remember, vector A to B is B minus A, vector C to D is D minus C. And now we get to this stuff. This is the more complicated side of vectors. So it looks like we may actually get a chance to do a little bit of it, although we've only got a few minutes left. We did start a couple minutes early, so we will try and go a couple minutes over for your sake, because that's how much we care. But I will try and give a very clear definition of how we deal with vectors, because a lot of people, this goes whoosh over their head. I really like vectors, this type of vectors, because I see it like a game. The game is, how do you get from one point to another point, in this part A to D, using only lines with arrows on? So, we need to get from point A up here to point D down here using only lines that have arrows on them, which means we cannot go across that line because it hasn't got an arrow on it. But we can use this line and any line that is exactly the same as that. And that's what's really interesting about this topic, about this particular question actually. Because it's a regular hexagon, that means all lengths are the same. That's what regular shape is, when all of the lengths are the same. A square is a regular shape. A rectangle is not a regular shape because it has different sized lengths. So a regular hexagon means all of these lengths are exactly the same. So that means that this length A here is exactly the same as that length there and exactly the same as that length there. So all of these three lines are all vector A. So technically, we can see them as lines with arrows on them because they are the exact same magnitude and direction. That's what vectors are all about. Then this line B is exactly the same as this line and this line. So I'm going to notate the A's and B's where relevant here. So because those lines are exactly the same magnitude and direction, they are the same vectors and we can use those lines. So getting from A to D now is a lot easier. We can do A to O to B to C to D. And then, so the way we notate that is from A to O, we go minus A. The reason why it's minus A is because we're going against the arrow, we're going the opposite direction of the arrow. So it's going to be minus A, then plus B because we're going along with the arrow, then minus A again, and then minus B because we're going against the arrow. So it's that direction there. Minus B. And then we simplify, the B's are going to cancel out, plus B minus B. Minus A is minus 2A. Now those of you who have done this before may have already noticed that actually we can, if this is length A, vector A, then because it's a regular shape it goes all the way through there, so that's also an A. So we could just go directly through there, minus 2A, all in one go. Now the more you practice these type of questions, the more, the clearer it will be that you can start to see these patterns and these trends and which lines are the same as other lines. But don't worry if you didn't see that straight away. You're not supposed to see it straight away. It comes with time. I'm going to get rid of a lot of this stuff because the page is looking quite messy, so we can go on to the next part. So let me eliminate all of these. Eliminate? Erase. Let's use that word. It's a nicer word. So now it's asking, find in terms of A and B the vector AB. So this one should be relatively straightforward. A to B, we just go minus A plus B. So remember, because we're going against the arrow, it's a negative, and then we're going with the arrow, it's a positive. So minus A plus B will be the answer to that one. And then find the vector AF. Don't forget, this vector here, this line here is the same magnitude and direction as this one, so it is a B in that direction. So AF is just minus B. Okay, pretty nice. Let's scroll on down to the next one. Parallelograms. They love parallelograms in vectors. They love triangles and parallelograms. The reason why a parallelogram is so important in vectors is because the opposite sides of a parallelogram are exactly the same. Same as a rectangle. A parallelogram is basically a rectangle that's sort of leaning to one side. So if we know, so AB is going to be exactly the same as CD, and BD is going to be exactly the same as AC. So that's really helpful for parallelograms. Also, another thing about parallelograms that's really helpful to know is that the two diagonals cross at their midpoints. So it doesn't say that in the question, but you're supposed to know that by the fact it's a parallelogram, is that this point here in the middle is the midpoint of CB and the midpoint of AD. And that's going to be really helpful for us when we're answering these questions. So, find in terms of vector A, the vector DA. So how do we get from D to A using only lines with arrows on? Well, because we are told that OA is 2A and OA, and O is the midpoint, that means DO is exactly the same vector. It's obviously going in the same direction, and it is the same length because O is the midpoint. So that means this is also 2A, meaning the answer is 4A. Find in terms of A and B the vector AB. Well, let me change the color on this. AB, we would go there and there, minus 2A plus 2B. And then the last one, find in terms of A and B the vector AC. Let's change the color once again. Let's go for a nice deep blue this time. AC, we would go minus 2A minus 2B, because that length there, CO, is the same as OB because of the midpoint. It's going to be minus 2A minus 2B. Okay. Now, those who've done vectors before may recognize this type of question more than any other. This is the typical vector style diagram for which we're going to answer the question. So, and actually this is going to contain a really, really important nugget of information that's going to serve you very, very well. So let's start off quite easy. Find in terms of A and B the vector AB. So once again, that is just how do we get from A to B using only lines with arrows on. That means ignore that line. It doesn't have an arrow on, so we don't care. The way we get from A to B is there, then there. Quite simply, minus 5A plus 3B. That is A to B. Find in terms of A and B the vector AM. This is the serious bit now. This is the important bit where this may change everything you know about vectors. This may make everything easier. This is where it clicks. If you're trying to find a vector that is part of the way across a line, don't. If you're trying to find AM, because that is part of a line, don't find it. What you want to do is find the entire line that it's on, then find the fraction of that line that you want. Now, I'll show you how we do it just to clarify that. If it's asking for a part of a line, AM, don't find AM. Find the entire line. The good news about that is we already have that. That's AB. So AM is half of AB. Now we can see that clearly now I've mentioned it, but that's something you're going to have to spot for yourself. Because M is the midpoint, AM is half of AB, so we're going to go that route. We know AB is minus 5A plus 3B, so we would write that as half minus 5A plus 3B, which is, and then we should do a half times minus 5, which is just half of minus 5, so minus 2.5A plus 1.5B. And that's a game changer for vectors as far as I'm concerned. Remember, I'll say it one more time. If you're trying to find a vector that is part of the way, part of a line, don't. Find the entire line and then multiply it by the fraction of that line that you want. That's going to make this last bit a lot easier now. Find in terms of A and B the vector OM. Now OM is the line from there to there. We're not going to do it that way. We're going to go from O up to A, down to M. So when we're finding vectors, we first of all decide the route we're going to take, and then we add those vectors together. So O to M is O to A plus A to M. O to A, quite simply from our diagram, is 5A. And A to M, we've just found out, is minus 2.5A plus 1.5B. And then we're just going to collect like terms on that. So 5A plus minus 2.5A, remember plus minus means minus, the negative wins in that battle. So that's going to be 2.5A plus 1.5B. And that is how we deal with those type of vectors. We don't have enough time, unfortunately, to go to the more complex ones, but I'll do my best next week. That's where we'll start from. So if vectors are a problem area for you, make sure you come in at the very beginning of next week's lesson. We will keep you updated on what time that will be, but it will be on Saturday. But thank you very much for joining us. That will be the end of it. If you have any comments or anything, just head over to ExamRiz or message me on TikTok at the fucking maths tutor. But yeah, thank you so much for taking time on your Christmas Eve. Go take a break, go have a rest, and enjoy Christmas guilt-free, knowing you have you've done your work for the next few days. What will you do is a question being asked. I assume you mean next week. Next week we're going to be doing vectors. Let me actually have a look. I do actually know what topics we're going to be doing next week. So let me say, so vectors, we're going to be doing similar shapes and maybe some transforming graphs as well. So if there are any other particular topics you'd like to take a look at, let us know and we'll do our best to include those. Just reading your messages now. You're very welcome, and yeah, have a great Christmas, and we'll see you next week. Bye bye.